Okay, we're going to finish up chapter 3. There are only 20 slides left, so I'm confident that this will be the last video. So we just finished talking about all the periodic trends in the periodic table and then getting a better understanding of the periodic table itself, how it was developed, and how the information is organized in it. So you want to think that the periodic table is a way to help us organize knowledge, not something you have to memorize or know what's in what column and things like that. So you'll always be able to have a periodic table on the test. So the last part of this chapter is now talking about molecular and ionic compounds. So we're essentially going to think about how bonds form. So we're going to define ionic and molecular, which are covalent compounds. We're going to predict the type of compound formed from elements based on their location in the periodic table, which will make sense because ionic compounds will form when ionization energies are low for the cation that you're forming, and then electron affinities are high for the anion you're making. So really we'll have a huge part of deciding when something will be ionic will be a difference in those two properties. So we're going to determine formulas for simple ionic compounds. So in ordinary chemical reactions, the nucleus of each atom and therefore the identity of the element remains unchanged. So in a chemical reaction, all we're doing is changing how electrons are interacting, not what the nucleus looks like. The very last week of the block, we'll talk about nuclear chem and think about things like fission and fusion and how we get energy out of the nucleus. But that's a whole different kind of reaction. So electrons participate in chemical reactions by being gained, lost, or shared. So, and those things will happen based on how easy it is to gain, lose, and share. So the gain or loss of electrons results in forming ions. So this is a picture of a sodium ion, and its outer electron is easy to pull off. It has a low ionization energy, so it's easy to make it into an Na plus ion, a cation. So the periodic table can serve as a guide for predicting ionic charge of main group elements. So many main group metals lose enough electrons to leave them with the same number of electrons as an atom of the preceding noble gas. So if you pull electrons off, you can create that same configuration as one of the noble gases, which we know is very stable. So if you lose one, you form a +1 cation. Those are always group 1 elements, because if you take one of their electrons off, it's in an s orbital that only has 1, and so then it becomes a noble gas. Whereas group 2, it has to lose 2 electrons in order to become a noble gas. So many nonmetals gain enough electrons to give them the same number of electrons as an atom of the next noble gas up. So if you gain 1 electron and you're in group 17, that's the halogens, then you're going to have a -1 charge. And if you're in group 16, it takes 2 electrons to get over to group 18, which is the noble gases. So you're going to have a 2 negative charge. And so if you think about it, +1 and +2 are about it. If you start taking more off, sometimes there are a few +3 and +4 cations, but remember that every time you take an electron off and the species left behind is more positively charged, it gets harder and harder to pull off an electron. And the same thing with electron affinity. As you stick electrons on, they start to repel the electrons you're trying to stick on, and so it's harder and harder to get more negative charge than a -2. So if we have calcium, it has 20 protons and 20 electrons. If it loses 2 electrons, it'll have 20 protons and 18 electrons, but that gives it the same number of electrons as the noble gas before it, which was argon, which has 18 protons and 18 electrons. Whereas bromine is 1 electron away, so it has 36 protons and 35 electrons. If it gains an electron, it's up to 36, and then it will look like krypton, a noble gas. So if we want to predict ion charge, if you move from the far left to the far right, the positively the positive charges of cations are equal to the group number, whereas moving from the far right to the far left in the periodic table, negative charges of anions are equal to the number of groups moved left from the Nobel gas. I think it's just easier if you look at this just to think. If you're in group 17, you're 1 electron away, so it's going to be a -1. If you're in group 16, you're 2 electrons away from neon, argon, the noble gases. So I think that's a little easier to think about than these first two rules. This method is less reliable for the transition metals. They have varying charges. So copper can be +1 or +2, iron can be +2 or +3. So their locations in the periodic table aren't as hard and fast in determining what cation or anion charge they're going to have. So if we have polyatomic ions, those are ions that are that we have discussed so far are just monatomic, so just a single atom. But you can also have polyatomic ions, so they're molecules are electrically charged molecules. So a molecule is something that has covalent bonds holding it together. But then if it has an extra electron, it could be a polyatomic ion that would be an anion. And if it has 1 electron missing, it could also be a cation. Oxyanions are polyatomic ions that contain 1 or more oxygen atoms. So they're just a special class of polyatomic ions. These are the polyatomic ions, and I would give you this table always. You don't have to memorize these. So just to realize that each of these are groups of atoms that are covalently bonded together, and then they either have an extra electron or more, or missing electrons. So we're not going to worry about how we name the oxyanions with the 8 and the ite. That's an old way to do it, and we'll use the common names in the table, but we're not going to go through how that naming system was developed. So when we think about chemical bonds, when electrons are transferred, ions are formed, and you get an ionic bond possible. Ionic bonds aren't the process of creating the anions and cations. They're the fact that once those species are formed, one's positive and one's negative. And so there's an attraction between those two. And that attraction, that electrostatic force between plus and minus, is what is the ionic bond. So when electrons are shared and molecules form, a covalent bond results. So when there isn't a big enough difference in the two atoms for one to pull off an electron and the other be left without one, they're going to share, and we call that a covalent bond. So compounds are classified as ionic or covalent. Molecular, so covalent and molecular are synonymous, and it's on the basis of the bonds that are present in them. So ionic compounds are usually formed from metals and nonmetals, because for metals, it's easy for them to lose electrons and form cations. And nonmetals, those things on the far right, it's easy for them to gain electrons and form anions. And then when a metal and a nonmetal react, you get that transfer of electrons. And then you can form the ionic bond once you have plus and minus. So a compound that contains ions and is held together by an ionic bond is called an ionic compound. So these are just some examples. Sodium is way far to the left. Chlorine is way far to the right. So when they see each other, sodium neutral and chlorine neutral, there's a favorable energy. If sodium gives up an electron, chlorine picks one up, and it forms the ionic bonds that hold sodium chloride together. Calcium and chlorine, it's similar, except chlorine has to give up 2 electrons. So chlorine, you have to have 2 of them pick up 1 electron. And so you get an ionic compound that's 1 calcium, 2+ cation, and 2 chlorine, single negative anions. So properties of ionic compounds, they're typically solids with high melting points and boiling points because those ionic bonds are super strong. They are non-conductive in the solid form, but if you make them liquid, either melt them or dissolve them, they become conductive of electricity. And this is just a picture of how you would measure that conducting of electricity. Essentially, by putting the light bulb there, you can show that there's electricity going through the wire as they move from the cations to the anions. So ionic compounds are electrically neutral overall. The formula for an ionic compound must have a ratio of ions such that the number of positive and negative charges are equal. That's why when we looked at calcium and chlorine, it didn't form CaCl, it formed CaCl2, because in order to make it neutral, you can have one of the calcium 2 plus, but you had to have two of the negative ones in order for that all to add to zero. And this is just giving that same example, but with aluminum oxide. So aluminum likes to be 3 plus, oxygen likes to be 2 minus. So in order to combine those in such a way to get zero, you have to have 2 aluminum cations and 3 oxygen anions. And this is just a picture of aluminum oxide. And it has some impurities in it to make it that really pretty purpley blue color. So many ionic compounds contain polyatomic ions as the cation and or the anion or both. And we treat polyatomic ions as discrete units. So if you have, for example, nitrate, which is NO3 minus, it's a unit that stays together. You're not going to pull that apart. So a parentheses in the formula is used to indicate a group of atoms that behave as a unit. So if you think about calcium phosphate, it's 3 calcium and 2 phosphates, but you have to put the parentheses around the phosphate because the PO4 minus is a unit that you don't pull apart. So that's showing you that you need 2 of that entire unit in order to balance the charge on 3 calciums. So molecular compounds, as we talked about, are covalent compounds. They result when atoms share electrons. They exist as discrete neutral molecules. They're usually formed by a combination of nonmetals. So when things have similar properties, ionization energies, and electron affinities, they're going to form nonmetals because neither one can pull an electron off of the other. They often exist as gases, low boiling liquids, and low melting solids. So when we get to the very last chapter, chapter 10, we're going to talk about how those properties of liquids and solids are related back to the properties of the molecules. Not really sure why they, oh, it's an exercise. It must be in the text. We'll look at it. They don't tell us what the question is. And then that's the end of the chapter. So we'll have to look at what that exercise 41 was trying to teach us. So that's the end of chapter 3, 4 parts.